Hello CSC ISC students of 5th semester, welcome to lecture 4 on automata theory and computability. So, if you remember the last lecture we spent time on designing the finite state machines. Finite state machines designing, as you must have found out that it is very creative and very interesting. So, you should try out a number of problems because of the paucity of time we will be able to do only a few problems here. So, now what we ended yesterday is that there are some cases wherein the finite state machines are difficult to construct. So, for simple things it is easy, but for somewhat involved problems the finite state machines are difficult to construct. So, what is the way out? So, we introduced you to the non-deterministic finite state automata, and then we have today we will be looking at some more examples of non-deterministic finite state automata, and also we will try to see that how to convert, given a non-deterministic finite state machine, to a deterministic finite state machine. How to do that? What is the procedure? So, that procedure we will see with a example. Now, today's agenda is this one. Now, to recollect yesterday's, so for example, if you want to write a deterministic finite state machine for L is equal to W element of A comma B star, every W ends in AB or BA. So, here though you can list it, what are the string to be accepted, what are the thing not to be accepted, then it becomes very difficult to guess how many states are required for this problem. So, this problem you will encounter in many more problems. So, today we will be writing a deterministic finite state automata for this problem. The next problem which we are going to take is again the third character, same L is W is an element of A comma B star, it is a third character from the right is A. So, third character can come after a very long time. So, you have to understand it is from right. We are all used to reading everything from the left. So, we know how to do it, but from the right it becomes very difficult. So, again this is another typical problem for which you will not be able to write it easily. Now, these two are representative problems wherein you will find it difficult to write a finite state machines. Now, we will see that how to write a non-deterministic finite state machine. For some examples we will see, then in the end we will try to convert a non-deterministic finite state machine to a deterministic finite state machine. The first and the foremost is this, yesterday I have discussed, just to recollect, the if you want to write a non-deterministic finite state machine for L is equal to, L is derived from W is an element of A comma B star, where every W ends in B. So, if you look at the language, you see that B, the simple thing to be accepted is B, because it ends in B, AB, 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 everything ends in B. So, these strings will have to be accepted. Then L complement not to be accepted, or here it does not end in B, B may be there, but it does not end in B. So, these things should not be accepted. So, how to go about deterministic? Very easy, you have written it yesterday in the last class. Then now this will look like this. Now, what is the, how does the a non-deterministic finite state machine will look like? It will look like this. Why it is? Because it should end in B, A plus B whole star, any combination of A and B, okay, including 0 combination, followed by ending with B. So, that should be accepted. So, if you understand the regular expression, it is very easy to write a non-deterministic finite state machine. For example, any combination of A will get translated like this, that is a state with A B. Here A can come, B can come, it can come in any order and all that. Any combination of A and B will be accepted by state 1. Now, when the B comes, it goes to state 2, which is a accepting state. So, this is a non-deterministic finite state automata, because you see that there are 2 transitions here, there is 1 transition here, there are no transitions here. That is what we said, that in the non-deterministic finite state machine, there will be, can have 0, 1 or more transitions. Here 0 transitions, here 1 transition, here 2 transitions are there, because there are only 2 alphabets. Now, our effort will be to convert this, and when we convert that, we should get back this, it should look like this. So, that is the then we will have a faith in the procedure. So, now our effort will be to do that. Now, before we do that, we will see some more examples of, you must get used to the concept of non-deterministic finite state machine, and you should be able to write the non-deterministic machines. Now, next thing, now we will see the other next problem. So, problem 2 is, the L is defined on A comma B star. For simplicity, I have taken all the languages are defined on A comma B star, where W contains A B. That means, it contains means it can come in the beginning, it can come in the middle, it can come in the end. So, if you just think a bit, then you will know that the regular expression, there can be any combination of A plus B can be there in the initially, then A B can be there in the thing, then afterwards again A B can come. So, this can be epsilon, this can be epsilon, simply A B can be accepted, this can be any combination. So, this is what, if you understand, then if you write a regular expressions, it is always very easy to write a non-deterministic finite state machine. Now, how do I write this? Okay. Now, as I have told you in the previous, any combination of A and B, simply you write a state and make it A and B, A comma B. Here A can come first, then B can come, then another B can come, another A can come. So, any combination will be accepted, followed by A B, then followed by again A B. So, that is a final state, it need not be there. Okay. So, this is a once it is like this, I mean the state transition to itself loop is there, that is not a, that it should, it must be traversed, it need not be. Okay. For example, simply A B comes with A B also can be accepted. So, these are some of the representative strings. The language, as you see, everything contains A B somewhere. It is not necessary that A B should be there in the beginning or in the end, it can be somewhere in the string. So, wherever A B is not there, for example, L bar A B is not there. So, the such string should not be accepted. So, this is the second example of non-deterministic finite state machine. Now, coming to the third example, write a deterministic is not the thing, non-deterministic. Problem 3, we have write a deterministic finite state machine to accept the language L is equal to A comma B star, every W ends in A B or B A. This is what I have already discussed. So, we will have this, you will have a trouble in guessing the number of statements. Therefore, so it will be, now if you try to write a regular expression for that, A plus B star, that means any combination of A and B ending with either A B or B A, either plus means any one A B or B A. So, this is another example wherein we will be looking at it. So, how to write the thing? Again, if you go back to the previous one, A plus B star gets transformed into a single state with A B like this. That means, any combination of A and B will be accepted. Now, the AB or BA. AB it ends in the final state, BA it ends in final state. So, this is how you should write the non-deterministic finite state machine for this problem. Now, the next one is next problem which we are going to think is we want to write a non-deterministic finite state machine where the W is from A comma B star and the third character from the right is A. So, see, as I have told you, this problem already I have discussed, very difficult for us to guess from the right, okay, from the left third character, second character, I think it is very easy to count and calculate. This will be again another difficult problem. So, how to write for this will be like this. Regular expressions, if you are looking at any combination of A and B star, then this is the third character from the right is A. Then the second character from the right, it can be A or B. The last character from the right can be A or B. So, this gets transformed into a non-deterministic machine like this. Any combination of A, B, here A only K is permitted, here A or B is permitted, here A or B is permitted, it reaches the final state. Now, if you look at it, the third character from the right, this is the first character, second character, third character is A. So, that will be A. So, this is how a non-deterministic finite state machine will be written. The next last example will be to write a non-deterministic finite state machine to recognize the language W equal to A comma B star, where W is made up of an optional A followed by AA, 0 or more B's. So, this you have to understand, because this is a worked out problem in the book. So, you can look at it. Now, I will explain that. Now, the AA, that is the first optional A is not there. Now, in the second case optional A is there. Then in the third case optional A is not there, two A's are there followed by B, and 0, 1 or more B's. B's are not a must. So, if you look at it, the compulsory thing is two A's also have to be there. First A is also optional. So, with this the language to be recognized is AA, AAA, AAB, all this will be recognized. Now, the what is not to be recognized? A single A is not a thing, this is optional, two A's are a must, and B is optional. So, it cannot start with a B, it cannot start with a B, all B's thing, B's are permissible, but provided at least two A's should be precede that, then only B's are permitted. All these are to be a thing. So, how to write a thing for that? See, this is this should be written A or epsilon, that is epsilon actually. So, A or epsilon, that means either a character A or it can be null, that is empty string, followed by two A's are a must, then followed by B star. B star means B can be 0, 1 or more B's can be there. So, what you see here is if you take epsilon, then AA will be the minimum thing. Here there are assuming 0 B's are there, then that will result in AA. Suppose you take the first A followed by two A's, then its second string will come. So, this way you should get used to the formation of regular expression given the problem. So, once the regular expression is done, it is very easy to translate it into a non-deterministic finite state machine. The next thing, it will be looking like this. The solution for this, the first one can be A or empty, A or epsilon, followed by two A's, 1A, 2A, 0, 1 or more B's. So, this indicates 0, 1 or more B's. The B's are not compulsory, B's can be 0. So, this is the non-deterministic finite state machine for the regular expression here. Now, we have seen a number of examples, 5 examples we have seen, and some of them are not there in the book. I have only one example. I have taken it from the book. That's for that I will tell you what is the reason for that. Always I want to give you more examples, whatever that is not worked in the book, so that you will have a number of examples will be there at your disposal. Now the next is a very important step. All of you must follow it. That is, we want to translate, convert or a non-deterministic finite state machine to a deterministic finite state machine. How to do that? Okay, this is in elsewhere it is called as the subset construction. Okay, so that term has not been used in this book, but anyway the basic philosophy will be that. Now you have to understand that you are given certain things. So known to unknown, you know everything about a non-deterministic finite state machine. Now you are required to construct a deterministic finite state machine. So here you have to understand that deterministic finite state machine means a machine is get defined by its parameters. Once the parameters are known, you can write a transition diagram. Is it's not a very difficult problem. So now you know everything about the non-deterministic finite state machine. You know how many states are there, what is the sigma, what is the start state, what is the how many final accepting states are there. Transition function, it is evident by looking at the transition graph, transition diagram rather. So now you know all the things about the non-deterministic finite state machine. So you want to construct the same 5 data about the deterministic finite state machine. If you are able to do it, then that is as good as a conversion. So now to understand this, we will take an example, simple example, that is given a regular expression a plus b star followed by b. That means what? Set of all strings ending in b. Okay. So it's a minimum string that is to be accepted is v. This problem we have worked out already, and I am taking this because we should, when you convert this into a deterministic finite automata, we should get the same as what we have solved earlier. Okay. Then our procedure will be correct. Now here if you look at it, k finite number of states are 1 and 2. Now sigma alphabet is a comma b. Now yes, start state is 1. Now subset a is a subset of k accepting states, only 2 is a accepting state. Transition function as indicated in the above figure, that is this is a the transitions are indicated here. Okay. Transitions are there, one transition, and there are no transitions here. So now you know everything. So we need to compute about the deterministic finite state machines. All these 5 parameters, if you are able to compute, that is a translation. Now you don't need to compute all of them. Okay. So you need to, because only 3 parameters you need to compute. For example, k dash, how many states are there, how many final states are there. I have given a k dash. Okay, that is just to differentiate from the non-deterministic machines parameters. Now delta dash. So k is the finite set of states. This is for k dash is the, that is for the deterministic machine. Sigma will be same, whether it is a non-deterministic or deterministic, sigma will be same. The start state also will be same. So you don't need to calculate 2 parameters. That means out of 5 parameters you need to calculate only 3. If you are able to calculate all these 3, that means you have converted. Now a dash is the subset of k, a set of accepting states. The transitions you must be able to calculate. So with these 3 parameters, if you are able to calculate, then the translation is over. Now how to do that? Okay, I have taken a simple example. So what I will do is, see the probably it will be very difficult for us to think. We will have this diagram on the board so that it is easier for us to construct, and I will write this diagram. NFA, okay, non-deterministic finite state machine is like this. Start state, there is a transition on A comma B and transition on B. This is state 1, this is state 2, which is a final state, and there are no transitions here. So, this is, so our aim is to calculate deterministic finite state machine equivalent, which should do the same thing, which should accept a set of all strings ending in B. That is the aim. So, how to go about it? See, here we know all the things, k, sigma, delta, A, okay, all the parameters we know. So, now here we do not have to calculate all the things, because the sigma and start state S will be same, I told you. Then we need to calculate only k, k dash, delta dash and A dash. So, if you are able to calculate this, these two will be same. The start state of a deterministic and that is non-deterministic state finite state machine will be same. So, you do not have to think. Now, the way of calculation will be projecting will be like this. Now, the no change, this is what I have already explained. Okay. Now, the next is to start with, you should start with a start symbol. So, that means you have to say that the start state of this is nothing but the start state of this. So, now what is the start state of this? It is 1. So, only thing is we write it as a set here. So, the start state of deterministic machine is same as start of non-deterministic machine. Therefore, it is equivalent to 1. This is where we start. So, this is considered as a active state. Okay, active state is 1. So, I have this thing. And first is you have to set of active states you will have to compute. So, first is the start state you have to, you will be there as one of the active state, that will be the only one, and consider one start state and see what are all the transitions that are possible. So, you need to calculate the delta dash of 1 on A, but how do you, delta dash is what you want to calculate. So, you have to take the help of delta and calculate this thing. So, if you look at it, 1 on A, it will be go to 1 itself, that is what is indicated here. Okay. See, we are computing from this, okay, and calculating. Therefore, if you are looking at it, delta star of 1 on A will be equal to, that is this calculation will be done with respect to this, and whatever 1 on A is what, it will go to 1 itself. So, this defines the delta dash of this machine. Okay. Similarly, you have delta dash of 1 on B. What is that? How to calculate? This is what we want to calculate, but for this you have to go to this 1 on B. 1 on B will go to 1 and 2. It will go to 2 states, 1 and 2. So, now you have set of active states. Initially you had only 1. Now, there are 2 thing. This was there already, this is exists. This is, you have to, this does not exist, you have to say add this. So, this is the procedure we will have to follow. Now, if you look at the slides, now this does not exist, you have to add. So, the active states are the start state and 1 2 will be added. Now, you have to take 1 2 now. 1 2 you have to take on A and B, what happens? For that you have to take delta. See, the difference is you have to take each one of the states separately. Delta of 1 A union delta of 2 A. You have to see delta of 1 on A will be 1 itself, that is what is indicated here. Delta of 2 on A, 2 on A is null set, there is no transition. Therefore, if you take the union of these two, that will be 1 only. Now, similarly, delta dash of 1 2 comma B can be calculated. Only in this slide I want to be explicit. Delta of 1 comma B union delta of 2 comma B, each one you will have to take separately. Now, if you look at it, 1 on B will be, it will go to 1 2. Then 2 on B, 2 does not have a transition, therefore 5, 1 2 exists. So, that means what? Both of them exist. That means when you are not able to add any state, new state to the thing, the algorithm or the procedure terminates. So, that means to say that we have already translated a non-deterministic finite state machine to a deterministic finite state machine. Now let us write the transition table and diagram and see whether it matches with our original solution. Now, if you write it, if you go back, see, that is, this is the delta dash you will have to compute, delta dash on A and B. Okay. If you look at it, delta dash on A and B, it will go to 1 and 1 2, 1 and 1 2. Now, similarly, delta, then next is 1 2 on A and B. A and B, if you look at it, it will go to 1 and 1 2. Okay, 1 and 1 2. So, this is the, now already we have, once you get the transition function, that means you have already number of states are specified, the transition things are transition function is defined. Now, it is only writing the diagram. Okay. Now, the question comes, as I told you, the start state of a non-deterministic machine and a deterministic machine will be same. So, there also it was 1, here also it will be 1, but final state you will have to look at it slightly different way. So, in the case of non-deterministic, finite state was 2. Now, here in case of this, you will have to see wherever the finite state of non-deterministic machine appears, all such states will become final states. Now, 1 2, here 2 is there, 2 was the final state of non-deterministic machine, therefore, this becomes the final state. So, with these two, this is the already translated. If you write a diagram, then it will look something like this. So, that will be 1 2, on A it will go to 1 itself, on B it will go to 1 2, on B again in 1 2, on B it will go to itself, and on A it will come back to 1. So, this is the same solution we got when we constructed the deterministic finite state machine directly, except that here the states are looking thing. This is only a labeling. So, it is looking at as in a set notation 1, set notation set containing 1 2, but this can be changed. That means, I can make I can call this as 3 and 4, it does not prevent me to doing that. So, now it is identical to, if I do that, then it will be identical to the original solution. So, this is the way, this is the procedure you will have to follow if you want to convert a deterministic non-deterministic to deterministic finite state machine. So, the procedure is very simple, you need to follow it, what is the way it has been done in the book. So, I am explaining the same way, it could have been done in some other book in some other way, but we have to follow this, because later on when a non-deterministic machine with epsilon comes, then you will have to follow the same procedure. So, if you follow this procedure, even if there is a epsilon transitions are there, which we will be taking up next, then also it will be, the procedure remains same and you will be able to get an answer. I suppose this thing is one conversion we have done, I suppose that is understood. Now, we will be doing today one more problem, wherein again we will be converting a non-deterministic finite state machine to a deterministic finite state machine following the same procedure, but the problem is somewhat involved, somewhat bigger problem. So, we said the set of all strings ending in BA or AB, I mean we could not guess it, that it requires 5 states. So, now that we are able to, now look at the regular expression A plus B star followed by any combination of A and B including 0 combination followed by AB or BA, not both, AB or BA. So, this is the non-deterministic finite state machine. Now, our aim is to convert it. This we are not able to do it. Now, through the non-deterministic way, we come to a deterministic solution. We will see how to do that. Now, again the same procedure will be followed. Now, to start with, the start state of the non-deterministic and the deterministic machine is same, that is 1 in both the cases. Now, the active state initially only the start state will be there in the active states, consider 1. Now, the 1 you have to look at on A and B what happens. Now, if you look at A, on A it will go to 1 and 2 and on B it will go to 1 and 3. So, that is what I have written. So, this is from the looking at the non-deterministic transition diagram. So, this defines the thing. 1 on A will go to 1 2, 1 on B will go to 1 3. So, these two states were not there, active states. So, we need to add them. So, active states should be updated. Now, 1 is there, 1 2 is there, 1 3 is there. Now, sequentially you should consider all the active states and look at their transitions, because they are going to be finally there in the deterministic machine. So, therefore, you must talk of all the transitions for any of these active states. Now, take up the 1 2, 1 2 on A, 1 2 on B. If you look at it, 1 2, how to find out? See, 1 2, 1 2, 1 2 and 1 2 on A, 1 2 on B, 1 2 on A, 1 and 2 on A, then it is a union. What happens on 1, what happens on 2, take the union of that. 1 on A it will go to 1 and 2, and 2 on A has no transition. That is why I have indicated that as 1 on A will go to 1 2, 2 on A will go to null state, empty state. Okay. So, therefore, the resulting will be 1 2. Okay. Now, similarly 1 2 on B, if you look at it, 1 on B will go to 1 and 3, okay, 1 and 3. Then 2 on B, 2 on B will go to 4. That is what I have indicated here. So, 1 3 4 will be union. I mean, you have to simply add, it is a set addition. Okay. Now, this 1 2 already exists. So, 1 3 4 is a new one. So, you have to add to the active states. So, once you do that, active states 1 3 4 will be there. So, we had considered only 1 1 2. Now, 1 3 we will have to consider. 1 3 if you are doing it, again 1 3 what happens on A, what happens on B, using the non-deterministic transition diagram you have to get it. So, again 1 on A you have already seen it goes to 1 2, and 3 on A, if you look at it, 3 on A will go to 5, 3 on A, 3 on A will go to 5. So, that generates 1 2 5, which is new one, it is not there in the already in the active states, therefore, it is to be added. Now, similarly 1 3 on B, 1 on B will go to 1 and 3, then 3 on B there is no transition. So, therefore, it will be only 1 3. If you add a null set, then that will become same as the original exists. So, that means you have to add 1 2 5. So, if you add 1 2 5, to the existing active states. Now, this many active states will be there currently. So, so far you have considered 1, 1, 2, 1, 3 you have considered. Now, 1, 3, 4 you have to, this is also one of the states of DFA. So, deterministic finite machine or DFA automata. So, now if you consider 1, 3, 4 on A and B, look at the diagram and write these things. 1 on A it will go to 1, 2. Then 3 on A it will go to 5 and 4 on A it will go to empty set. Now, that will create a 1, 2, 5 that exists already. Now, 1, 3, 4 on B. Look at the transition diagram of non-deterministic. 1 on B, what happens? It goes to 1 and 3. Now, similarly 3 on B it will not go anywhere, therefore 5. Then 4 on B it will not go anywhere, 5. So, 1 3 already exists, this also exists. So, no need to add any new state. Now, coming to the next slide. Now, last 1 to 5 is the one of the active state for which we have not calculated delta dash. So, delta dash we have not calculated. So, for that purpose let us see how to do it. So, same procedure, 1 to 5 on A, 1 to 5 on B. Here I want to say that if there are 3 alphabets are there, then you will have to say 1 to 5 on A, 1 to 5 on B, 1 to 5 on C, you have to do it. So, this procedure is to be followed for whatever the number of alphabets are there in that language. So, now if you look at it, 1 on A, 1, 2 it will go, then 2 on A it will not null set, 5 on A null set. So, the 1, 2, 5 exists. Then if you look at the other one, 1, 2, 5 on B, 1 on B it will go to 1, 3, then 2 on B will go to 4, then 5 on B. If you look at the diagram of non-deterministic machine, then it is null. So, 1, 3, 4 all are existing. So, you have considered all the states for the transition function and nothing is getting added. So, no new states are added. So, procedure terminates. So, therefore, write the transition function. Now, you know everything. So, these are the active states are the states of the deterministic finite state machine. All the deltas are here. Once you know what are the number of active states and the transition function is there, that completely defines the deterministic finite state machine. So, now let us see how it is done. So, now if you the question is now this slightly see here, if you look at it, 4 and 5 were the final states of the non-deterministic machine. Now, if you look at how to decide, wherever 4 and 5 appears, they will become final states. So, that is why these two will become final states. Initial states of deterministic and finite state machine, the non-deterministic are same. So, that will remain 1. So, all these transitions are taken from this. If you look at it, 1 on A go to 1, 2. So, if you look at 1 on A, it will go to 1, 2. On B it will go to 1, 3. All the things which you have already calculated, I have put it in the form of tabular form. When this is given, this is calculated, it is as good as it is converted to deterministic finite machine. So, if we want, we can write the transition diagram. If we do this, then the transition diagram will look like this. Now, what it says, set of all strings ending in AB. So, it must accept AB, AB it accepts, then BA it accepts. Suppose we take some long string, for example, BB, AB or BA, BA. So, 4 B's followed by BA is there. So, for example, this is 1 B, 2, 3, 4 and 4, 5, then A, it comes to final state. So, that way it will this why this is important is, you would not be able to compute this all the transitions, slightly it will be involved, it will be difficult. So, if you take this path, that is write a non-deterministic finite state machine, then convert it to a deterministic finite machine, then it will be very easy to do it. So, this is evident from this problem. See, last problem was very easy, you could do it directly, but this was slightly involved problem. So, but that we have been able to do this. Now, again I will say the same thing, that is the states are looking as the sets. So, there is nothing to worry about it, you can always change these to some 1, 2, 3, 4, 5, 6, like if you want you can replace those set values by 1, 2, 3, 4, 5 like this. So, you can I mean it hardly matters whether you call this is 4 or 1, 3, 4, it really does not matter, it is only a name. So, what is the name? Well, there is nothing I mean. So, you can call by anything, but the function remains same. So, this is how, this is the procedure I want you to follow it and do it for, see, this is all the problems today what we have attempted is all are of the type wherein there are no epsilon transitions are there, not there. So, epsilon transitions also follow the same method, but it will be slightly a different way. So, that I will be completing that one in the next class, that is our 5th class, I will be doing that. Now, if you are looking at now what I want you to do is, now I have attempted only 2 problems. So, whereas many of the problems which you have, see for example, this is there, problem number 2, I have not solved this. So, this is a non-deterministic finite state machine. So, you need to convert this into a deterministic finite state machine. If you want that procedure to be clear, you must be able to get this. This is again another simple procedure, and for this you know the solution also, because this is nothing but containing A B, which we have done it. So, you know that it is self checking, in the sense you convert this into deterministic finite state machine, you check with your original answer and it should match. Okay. Now, if you want to start this thing, again the same procedure will be there. That means, for this is a non-deterministic finite state machine for which you have all the 5 parameters defined. Then for the deterministic one, you have to define only the number of states, the transitions and final states. Okay. That is how. Again you have to start with the active state equal to 1, active state of non-deterministic finite machine and the deterministic machine will be same. Then you have to look at the transitions, what are how 1 on A, 1 on B, how it will be. So, it generates the new states. If it is not there, then you will have to add that. So, this is the subset construction, it will go on adding that, sometime or the other there will not be a new state to add, then the algorithm will terminate. So, this is the method of doing it, and for this problem you must attempt it. I will give the solution to this one in the next class before I start the thing, then but you must attempt it. Now, the another problem, this we have worked it out, A B and B A ending in. Now, this problem, see for example, this is a very interesting problem, you must attempt it, then I will give the solution in the next class. That is the regular expression wherein the third character from the right, very important, is A, it should be N. So, here also you must here there is no epsilon transitions are not there. So, therefore, you can follow the same procedure what I have done it for the 2 problems. So, to your homework will be, you will have to do it for the 4th and 2nd problem, you have to convert it to a deterministic finite state machine, and the solution for which I will be giving it in the next class. So, now to summarize what is that you have done is, that is we have you must have understood, to write a non-deterministic finite state machine, the first and the foremost important thing is to understand the regular expression, because regular expression crystallizes the problem, then it will be very easy to write a non-deterministic finite state machine. You must practice the regular expression taking more examples. So, 4 examples of this thing I have given it. Now, then conversion procedure I have listed it out. So, that is you will have to follow the same procedure, and the same procedure will be following even for the epsilon transition is there. That is what I mean to say is, for example, this procedure will be slightly different for when there is a epsilon is there. So, for example, in the one which I have indicated, one wherein epsilon transition is see, when epsilon is there, it will be for example, this problem you cannot do it in the same way as we have done it today, because here there is 1 to 2 epsilon is there. If when the epsilon is there, then a new concept is brought in, that is what is known as epsilon closure will be brought in, that will have to be applied. This problem, that is why problem 5 I have not given it as a homework. So, problem 5 you cannot work it out. So, that I will indicate it in the next class. After that you will be able to work this problem. So, now coming to the today's thing. So, conversion of the remaining problems 2 and 4 you should attempt it, and the homework, convert all the problem number 2 and 4 into deterministic thing. 5 requires different, I will be explaining, as I have told you, that I will be discussing in the next class. I will give the solution for the 2 and 4 also. Now, if you have any questions on the there must be a lot of questions. You must follow the book. I have followed the procedure in the book. Actually, in some other book it may have done in a different way, but effectively all are mathematically equivalent. So, the procedure what I have explained is same as what is done in Ullmann or somewhere else, because the procedure has to be, only the way of projecting it is different. So, if you have any problems and all, then you can send me a mail, I will try to answer. Thank you.